Okay, so here is our first lecture for Gen Chem 2. We're going to talk about phase diagrams and crystalline solids. We're just going to kind of do a basic overview of them. You might see one or two questions about the calculations within your mini quizzes in your exam, but let's just dive in. So if you remember from the end of Gen Chem 1, we kind of touched on phase diagrams. And what you can see is that with these, sorry, didn't mean to do that. With these phase diagrams, they're basically like this Y-shaped diagram. Well, this is really bad. You're going to find my drawings are just fantastic. Okay. They're kind of like this Y-shaped diagram where we have different areas in which different things are in different phases. So this right here is what we call the triple point. And at that point, we have our biggest separation of solids, liquids, and gases. So this line right here, that is our sublimation curve. So all that means is when a solid completely goes right to a gas without any liquid phase. The best example of that, gosh, probably your grandma's mothballs. A lot of people used to put them in their closet as a way of absorbing moisture. Also, a lot of people use them, like if they live out in the country, they'll use them around the perimeter of their yard to keep snakes out. Mothballs, if you put them out, they will go completely to the gas phase, and there's never like a liquid residue on the floor. They start off as a solid, almost looks like kind of like a cotton ball, and then just goes right to a gas. There's no liquid phase there. Here we have our fusion curve, okay? And our fusion curve literally is showing where a solid melts into a liquid. So if we're looking, we're going from left to right, our solid is going to melt directly into a liquid. Here we have our vaporization curve, and that's when our liquid will go right into the gaseous phase. And you can see that it kind of goes up and up and up because that means a couple of things. Either the temperature is increasing or the pressure is increasing, depending. So the higher the pressure we have, the more solid liquid formations we have. The lower the pressure, the less interactions the molecules have amongst themselves. And then, of course, the higher the temperature, it should make sense that solids are going to go from a solid to a liquid to a gas, or straight from a solid to a liquid. By the way, this sublimation curve also happens to be our deposition curve, where sublimation is going from solid directly to a gas. I think I just said liquid, but you know what I mean. And the deposition curve is literally the gas going back directly to a solid. Best example of that, of deposition, is if you open your freezer and you see on the side walls of your freezer that there's those little crystals that form. What's happening is the water vapor in the air is crystallizing immediately as soon as it hits the walls of your freezer every time you open it. So ice crystals on your freezer, best example. Oh, a couple other things. Sorry, critical point, forgot that one. So your critical point is right here. And you'll notice that this one leg of the Y just kind of stops. And then there's this whole like area where you're kind of a liquid, kind of a gas. If I could put them in a chamber, what we would see happening is first there would be a phase where we would clearly see the water level and clearly see the vapor level with a defined line. At that supercritical fluid critical point, what we would see is that line between the gas phase and the liquid phase would disappear into each other, okay? So if I'm looking at a phase diagram, I need to be able to say, okay, so let's look at A right here, okay? Where it is drawn currently on our phase diagram, it is in a liquid phase. But if I decrease the temperature and make the temperature go down to say 0, it's going to form into a solid. If I increase the temperature, say to 110 degrees Celsius, we're going to go into our gas phase. So being able to read these phase diagrams is very important. Here's just an example of the difference between iodine and carbon dioxide. You can see that at different phases and different temperatures, they are going to behave differently. They're either going to be a solid, a liquid, or a gas, and their temperatures widely vary. Okay, so when we're talking about carbon dioxide being a gas here at, I don't know, maybe 10 degrees Celsius, when we're talking about iodine being a gas, we're talking about well over 184 degrees Celsius. So looking at this example, when it says what transition occurs when if a sample of carbon dioxide at negative 60 degrees Celsius, so we're going to say, okay, here's negative 60 degrees Celsius, at 10 ATM, so here's 1, 5, so we'll say maybe 10 ATM right there. We should expect it to be in the solid phase. So when it's warmed to 30 degrees Celsius, maintaining our 10 ATM, we should expect it to phase change into the gaseous phase. So why? Why is all this happening? The answer is the crystalline structure. What does that mean? Number one, it's structure. When you did Gen Chem 1, you did Lewis structures, you did their shapes, their molecular geometry, their electron pair geometry, and we found that based on their molecular structure or electron pair geometry, that determined polarity, and polarity determined behavior. So structure determines the properties of these solids. So how this right here, how the individual molecules arrange themselves is indicative of properties. It will allow us to better understand their behavior. So for example, ice. We talked about this when we talked about hydrogen bonding, or you should have. So if you remember, water is very polar, but it also hydrogen bonds because of those lone pairs. We have a partial negative on the oxygen, partial positives on those hydrogens. So we're going to get an attraction between the partial negative of the hydrogen end and the partial positive of the hydrogen end and the partial negative of the oxygen end. And that's going to be true of all water molecules. So what we get are kind of these spatial things going on, so that when water freezes and becomes ice, the spaces maintain their space, kind of like freezing in space. When that happens, that's one of the reasons that ice is less dense than its liquid counterpart water. So this repeating pattern that we get allows for ice to float because it's less dense, because there's more spaces between the molecules of the water, the H2O. So we're going to talk briefly about X-ray diffraction. You just kind of have to understand it on a very definition base. So with X-ray diffraction, all that is doing is, by way of bending light, It's allowing us to understand how these crystalline solid formations are put together. It allows us to see the molecular arrangement and measure the distance of the molecules in that solid. So when we talk about these crystalline structures, there are three we're going to focus on. The primitive or simple, the body-centered, and face-centered cubic cells. Conceptually, they're a little bit hard to visualize, and this is why we're going to watch these short videos, because the 3D animation of it is not one that I can replicate, and B is a good explanation of the body-centered cubic structure, which is really, really important. We're going to focus more on the body-centered than the face and simple. So let's start with this one.
If you could travel within a crystalline solid, you would see the particles, atoms, ions, or molecules arranged in a regular array. Here, the spaces are greatly exaggerated, but in reality, the particles are packed close together. The unit cell of a crystal structure is the smallest portion that defines the structure. Stacking unit cells next to each other in all three directions gives the structure. Many elements and simple compounds have unit cells from the cubic crystal system. Let's examine the three types of cubic unit cells. All cubic unit cells have particles at the corners of a cube. The simple or primitive cubic unit cell has particles at the corners only. In reality, the particles lie as close to each other as possible. Note that the particles touch along the cube edges, but not along a diagonal in the face or along a diagonal through the body. By slicing away parts that belong to neighboring unit cells, we see that the actual unit cell consists of portions of the particles. When the cells pack next to each other in all three dimensions, we obtain the crystal. If we fade the others out, you can see the original group of 8 particles within the array and the unit cell within that group. We find the number of particles in one unit cell by combining all the particles' portions. In the simple cubic unit cell, 8 corners, each of which is 1/8 of a particle, combine to give 1 particle. A key feature of a crystal structure is its coordination number, the number of the nearest neighbors surrounding each particle. In a simple cubic array, any given particle has a neighboring particle above, below, to the right, to the left, in front, and in back of it for a total of 6 nearest neighbors. The body-centered cubic unit cell has a particle at each corner and one in the center, which is colored pink to make it easier to see. With full-size spheres, you can see that the particles don't touch along the edges of the cube, but each corner particle does touch the one in the center. The actual unit cell consists of portions of the corner particles and the whole one in the center. 8/8 give 1 particle, and the one in the center gives another for a total of 2 particles. In this tiny portion of a body-centered cubic array, you can see that any given particle has 4 nearest neighbors above and 4 below for a total of 8 nearest neighbors. The face-centered cubic unit cell has a particle at each corner and in each face, which are colored yellow here, but none in the center. The corner particles don't touch each other, but each corner does touch a particle in the face, and
when we're talking about the face, if you can imagine an actual cube, the blue ones would be in the corners of that cube. Again, imagine like a Rubik's Cube, right? So the blue spheres would be on the corners of that Rubik's Cube, and the yellow ones would be on the face where the colors are of the Rubik's Cube. Nothing in the center. Unlike the body-centered unit where the pink one, I think it was pink, it would be like in the dead center of the Rubik's Cube, and the blue ones were only on the corners.
Those in the faces touch each other as well. The actual unit cell consists of portions of particles at the corners and in the faces. 8/8 at the corners gives 1 particle, and half a particle in each of 6 faces gives 3 more, for a total of 4 particles. In this tiny portion of a face-centered cubic array, notice that a given particle has 4 nearest neighbors around it, 4 more above, and 4 more below, for a total of 12 nearest neighbors. Stacking spheres shows how the 3 cubic unit cells arise. Arrange a layer of spheres in horizontal and vertical rows. Note the large diamond-shaped space among the particles. Placing the next layer directly over the first gives a structure based on the simple cubic unit cell. Those larger spaces mean an inefficient use of space. In fact, only 52% of the available volume is actually occupied by spheres.
Think about if you had 18 eggs, right? But you only had a 12-holder egg carton. If you were going to stack those eggs, it is less efficient to put one egg on top of the other as opposed to offsetting them. So the second row of eggs could go into the spaces between the first row of eggs. In the simple cubic unit, that is not the case. The eggs are stacked one on top of the other. That will change with body-centered and face-centered units.
Because of this inefficiency, the simple cubic unit cell is seen rarely in nature. A more efficient stacking occurs if we place the second layer over the spaces formed by the first layer, and the third layer over the spaces formed by the second. That simple change leads to 68% of the available volume occupied by the spheres and a structure based on the body-centered cubic unit cell. Many metals, including all the alkali metals, adopt this arrangement. For the most efficient stacking, shift every other row in the first layer so the large diamond-shaped spaces become smaller triangular spaces, and place the second layer over them. Then the third layer goes over the holes visible through the first and second layers. In this arrangement, called cubic closest packing, spheres occupy 74% of the volume. Note that it is based on the face-centered cubic unit cell. Many elements, covalent compounds, and, as you'll see in the next 2 examples, ionic compounds adopt cubic closest packing. Sodium chloride adopts the sodium chloride or rock salt structure, as do many other alkali, halides, alkaline earth oxides, and sulfides, and other ionic compounds. Picture separate face-centered cubic arrays of chloride ions and sodium ions as they approach and interpenetrate each other. The smaller sodium ions fit in the holes between the larger chloride ions and the NaCl unit cell.
Now, if you remember from Gen Chem 1, sodium is all the way in group 1 on the left-hand side of the periodic table, and the chloride ion is all the way in group 17 on the right-hand side of the periodic table. And what we learned was that the atomic radii increases as you go up the periodic table and to the right, but chloride ion is significantly larger than the sodium ion. It is way further down, and yes, it's all the way over to the right, but it's way further down compared to sodium. And if nothing else, their molar masses are completely different and far off, so that one is going to be significantly larger than the other. So because the sodium is much smaller than the chloride ion, the sodium is able to easily and readily fit into those spaces that the chloride ions pack in there. And that's why when we said ionic compounds such as sodium chloride, when they formed, they had this repeating geometric pattern of kind of an alternating tongue and groove fit, if you will.
Zinc sulfide adopts the zinc blend structure, as do the copper-1 halides and several other compounds. If face-centered cubic arrays of zinc ions and sulfide ions approach and interpenetrate slightly offset from each other, each ion becomes surrounded tetrahedrally by 4 of the other ions. Note the blinking zinc ion and the 4 sulfides. You can see the relative positions in this slightly expanded view of the zinc blend unit cell.
Okay, so when you're done with this lecture, go ahead and watch part B. It's the math behind figuring out how to figure out densities of the different compounds that come together outside of when we learn just generic, density equals mass divided by volume. It's literally looking at what type of what type of unit cell it is and how to mathematically calculate what you're looking at. So with all these unit cells, there's a couple of things you need to know. So the first thing you need to know is that the length of each side is 2r, okay? R being the radius. Okay, so remember with simple cubic, if we were talking about a cube, the atoms were only on the corners, nothing in the middle, and nothing on the faces. So with 8 corners, each molecule, or each portion of that molecule, is 1/8 of a whole. And there are 8 of them to give us one whole atom. So this generic chart you need to know. So this column right here is going to tell you how to calculate the edge length, so the length of each edge. So for simple cubic, it's 2r. For body-centered, it's 4r divided by root 3. And for face-centered, it's 2 root 2r. So the coordination number, as it was talked about in that video, is just the number of oppositely charged ions, an ion that is in contact with the faces of the cube. All right. The higher the coordination number means the more interaction or touching of the molecules that are present, meaning the more compact they are and the more efficiently they are stacked. And then packing efficiency is literally just that. How efficiently have you packed the unit cells so there's the least amount of empty space there. So with the cubic unit cells, you have to know that there's all 90-degree angles. And we know that we have an eighth, a 1/2, and a 1/4, depending. This is going to be for your simple. This is going to be for your body-centered. And this one is going to be for your face-centered. So these are just examples that you can go through to determine many things, the coordination number, how many particles are there, and let's see, edge of the unit cell, like the length of it. And this is just simply for the simple cubic unit cell. If we look at the body-centered cubic, now there's a couple of things going on here, and I have included in this PowerPoint a thing I drew up, but it relates to video B that you need to go watch when you're done watching this lecture. And I will upload it as a PDF. I'm pretty sure I still have it as a PDF. If not, I would go ahead and print it out from these PowerPoints. It's a couple of slides down, and I'll mention that when we get to it. So if you were talking about with this particular body-centered cubic cell, if you remember, there's one length, here's another length, but these are perfect cubes. This is a 90-degree angle. So B, in this case, would be our hypotenuse. Okay? Now, if we use Pythagorean theorem, we can figure out all the information we need to know about this. So let's just look at an example. This is the handout I was referring to. I will go ahead and upload this. All right, so a body-centered cubic cell unit has a volume, oh, sorry, my camera's in the way, 4.32 times 10 to the minus 23 cubic centimeters. Find the radius of the atom in, wow, words are hard today, y'all, of the atom in picometers. So first, we're going to convert the volume. You know this is a volume because of the unit. The cubic centimeter immediately should tell you volume. We're going to convert that to length, because remember, volume of a cube is length cubed. Length times length times length. If it were a square, it'd be length squared. But this is a cube. So length times length times length. So we're just simply going to take the square root of the given volume. I'm sorry, the cube root of the given volume. Once we have the length, we can solve for the radius by using the equation that was associated with a body-centered cubic cell. So take the cube root of the 4.32 times 10 to the minus 23. That's going to give us 3.5088 times 10 to the minus 8 centimeters. Now, when you're putting this into your calculator, you are going to go to Math, and I'm assuming all of y'all have some sort of TI 84, 85, 89, something like that. So this goes with that style of calculator. If you have something lower than that, or if you have like a Casio or something, I'm not going to be much help for you. You might need to Google it. So you're going to hit the Math button. Then you're going to go down to number 4, which is the cube root. And this will pop up on your screen. Okay, so I'm doing this. Oh, I'm doing this as I go through with you. Okay, now it'll show up like this on your screen. So you need to maintain that parentheses 4.32, and this is what you're going to type into your calculator. The second button, and then the EE button. The EE button is the comma once you've hit the second button. The comma is right above the number 7. And then only the power. And then you're going to close those parentheses. What that's going to look like on your calculator screen is this. Okay? So then you're just going to hit, of course, answer. And it's going to give you this number. All right? Now, that number is going to be used to get plugged in to R, because, I'm sorry, I said that backwards, to L. Just kidding. To L. And we're going to solve for R. We don't know what the R is. That's what we're solving for. So if you were to rearrange this equation, and I'll just do that math real quick. Now, when you type this part into your calculator, use parentheses, okay? Parentheses are your friends. Your calculator orders strictly by order of operation. So if you're not using parentheses, you don't want to tell your calculator the length times root 3 over 4 or something like that, okay? You want the length times root 3, whole thing divided by 4. So once you plug all that in, this is going to be your answer, and you're going to have to convert centimeters to picometers using the metric system. So here's just another example. This AB pattern, what you need to take away from this is that it's that staggering effect of how to pack. Not just so, you know, we not only want to stagger the rows instead of like doing this. This is where that diamond shape came from. Remember, he talked about getting it so we would not have this diamond space, but we would have instead this triangle space. The triangle space is a much smaller space than just literally linearly stacking them. So not only do we want to stagger the bottom layer, but we're going to stagger the top layer also. So we're staggering each layer and then staggering those layers onto each other. So now we've gone from a diamond to a triangle to this teeny tiny little spot here. That's all we got left between them. And that's what we want. That's the most effective, efficient way of packing. So this is all for part 1. I will go live with part 2 on Wednesday.